Okay, so now we just want to work a little bit more to discuss what Lie algebra this is. Okay, so the first thing that we're going to do is we're going to count the number of parameters. So let's say so we want to count the number of parameters, and by now I think this is quite simple for you. So remember we have translations. The parameter was a alpha, and there are d of these. Then we also have special conformal transformations. The parameter is b alpha, there are d of those. We've got scalings. The parameter is lambda, there's one of those. And then we've got Lorentz transformations. And you know that Lorentz transformations are rotations and boosts. We call these omega alpha beta. And if we are working in d space-time dimensions, this was d times d minus 1 over 2. So let's now work out what is the total number of parameters in the conformal group. So the total is equal to, it'll be d plus d, that's 2d, plus 1, plus d times d minus 1 over 2. Let's put everything over 2. So if we put everything over 2, d times d, that's d squared, minus d. The 2d will become plus 4d, and plus 1 will become plus 2. And if you take a look at what that is, that's d squared plus 3d plus 2. Well, that's just d plus 2 times d plus 1 over 2. So that's the total number of transformations in the conformal group. And of course, we're taking d greater than 2. You know that with d is equal to 2, there were an infinite number of transformations. Okay, so how do we identify this group? Okay, so we're going to start doing, just develop a little bit of notation, just so that you know the names of a few groups. So let's look at d is equal to 3, and we will talk about Euclidean spacetime. In this case, the metric of the space is dx1 squared plus dx2 squared plus dx3 squared. One isometry that we have of the space, so one isometry that we have is SO3. Okay, just rotations in 3 dimensions. And if you ask how many rotations there are a total of 3 rotations. Now, let's just talk a little bit about where this 3 comes from. 3 dimensions is like the 3 dimensions of our world. You might think that you're rotating about X, rotating about Y, rotating about Z. That's the wrong way of thinking. We always rotate in a plane. Rotating about an axis is special to 3 dimensions. So because we rotate about a plane, there's 3 rotations. What are we counting? We're counting the number of planes. And in d is equal to 3, we've got the 1, 2 plane, we've got the 1, 3 plane, and we've got the 2, 3 plane. So we've got a total of 3 planes. If we were in 2 dimensions, so let's just do 2 other examples. Let's say we were in 2 dimensions. So over here we could put x1, here we could put x2. We still have rotations. A rotation would move a vector around, for example, counterclockwise about the origin. So if I had some vector here and I did some rotation, it would be transported to there. Now, I can't think this is a rotation about any axis. There are 2 axes in the space, the 1 axis and the 2 axis, and this is not a rotation about the 1 axis or about the 2 axis, but it is a rotation in the 1, 2 plane. Similarly, if we were to look at d is equal to 4, well, in d is equal to 4, we've got the 1-axis, the 2-axis, the 3-axis, and the 4-axis. And if we want to count how many rotations there are, we count the number of planes. So there's the 1-2 plane, there is the 1-3 plane, there is the 1-4 plane, the 2-3 plane, the 2-4 plane, and the 3-4 planes. Okay? You can see there's a total of 6 planes. So there's a total of 6 rotations. Now, how do we get this 6? Well, it's quite easy. So we can talk about the AB plane. Okay? So thinking about the AB plane, we can pick A to be any one of D. We can pick B to be any one of D minus 1. So when we specify a plane, the 1-2 plane or the 2-4 plane, what's important is the two axes that we picked must be distinct. We can't have the 1-1 plane, but we can have the 1-2 plane or the 1-4 plane. So there's D times D minus 1 choices of A and B, but, and this is something to pay attention to, but the AB plane is exactly the same thing as the BA plane. So we shouldn't count the AB plane and the BA plane independently. So the number of planes is equal to D times D minus 1, and then we divide by 2 for this fact over here. That's why we are dividing by 2. And you can check that in D is equal to 4, we've got 4 times by 4. This should be minus 1. We've got 4 times 4 minus 1, which is 3, divided by 2. That's 6. Good. Now notice something. 6 is also the number of Lorentz transformations. But when you're thinking about Lorentz transformations, you're not thinking about space like Euclidean space, rather you're thinking about space-time. So you're thinking about 4-dimensional Minkowski space. So in that case, you've got ds squared is equal to, you'll have a minus dx naught squared. You'll have plus dx1 squared plus dx2 squared plus dx3 squared. Okay? And you can pick the opposite sign convention if you like. That's what I picked up for Minkowski space. There's still 6 Lorentz transformations. In this case, how would we write this group? We would still write it as SO, but now we would write 1, 3. 1 because there's one direction in the metric, which has a minus sign, and 3 because there's 3 directions in the metric that have a plus sign. Now, when you count the number of generators in SO13, you're used to saying that there are rotations. You'll count rotations just like we did above. So you could do it in the 1-2 plane, in the 1-3 plane, or in the 2-3 plane. So this is like counting planes. But then when you count boosts, you're probably used to thinking about counting a boost along 1, or a boost along 2, or a boost along 3. But if you think about it a little bit, boosting along 3 is like, it's related to doing a rotation, okay, complexification of a rotation, but in the 0-1 plane. Boosting along 2, you're doing something in the 0-2 plane. And boosting along 3, you're doing something in the 0-3 plane. And that's why we still get 6. So we can still count the number of transformations in SO13 by counting planes. And in fact, if you had the group SO1D, how many parameters would you have in this group? Well, you would have D plus 1 times by D over 2. So just like the counting for SOD. Okay, so maybe let me put SOD plus 1 just down below. So with SO1D, one of the directions would have a minus sign. For SOD plus 1, all of them would have plus signs in the metric. But for SOD plus 1, you would take D plus 1 times by D over 2. So that counting is always the same. Now, I'm sure that by now you have thought about the natural generalization. The natural generalization would be to take a metric ds squared, which is minus dx1 squared minus dx2 squared, keep going, minus dxn squared plus dy1 squared plus dy2 squared plus dym squared. So here there would be lots of time directions you could use to do boosts. You could do rotations between the different time directions. You could do rotation between the space directions. So big group. What do we call this group? This would be SON, because there's n directions with a minus sign, M, because there's m directions with a plus sign. And what would be the number of parameters? Well, number of parameters, well, what you would do is you would take n plus m, that's the total number of directions, times n plus m minus 1 divided by 2. So it's your usual counting for an SO group. Okay, so this is just a little generalization of the SO group. So that's what we want. Now, let me tell you what the conformal group is. So the conformal group in D dimensions is, it is SO2, D. So what's the number of parameters? Number of parameters, well, this would be d plus 2 times by d plus 1 over 2. And that counted the number of parameters that we got when we just counted the number of parameters in the conformal group. So that's what the conformal group is in D dimensions. So for example, in 3 plus 1 dimensions, the conformal group is SO2, 4. This would be relevant for our world if there was conformal symmetry in our world, and you also had Poincare symmetry. You can also have conformal symmetry in non-relativistic systems, but here we're talking explicitly about a relativistic system. It's not good enough to just count the number of parameters and show that the number of parameters match. To really prove that you have the same Lie group, you would need to explain how the elements of the Lie algebra of the conformal group that we constructed above is related to the elements of the Lie algebra of SO2, and you would need to check that their commutators come out correctly. So that's what we're going to do next, and that'll finish off our discussion of the conformal group.